Good morning and welcome to the Automation Academy's Mastering the Machine webinar. This is the 88th webinar of this name for the 12th of July 2025. Our topic today is PLC history. We're going to be going all the way back to and a little bit before the invention of the PLC, which was in 1968. But before we do that, let's get through some of the basics here. What is the Automation Academy itself? The Automation Academy is a subscription-based website that has lots and lots of information, training videos for Allen Bradley, Siemens, Beckhoff, Omron, a little bit of Automation Direct, Code Assist, that sort of thing. We do have some job and aptitude assistance videos from the Ken Coleman program. Have lots of systems integration tips, lots of videos, a big library of training and technical documents, some software on there that you can download to practice PLC programming. We do have a community with some interest groups, IO Central, and that is open to anybody. You do not have to be a member to access IO Central. We do have these regular events, Mastering the Machine webinars. This will be changing a little bit, and I'll describe how that is and why that is a little bit later. You can find all this information at automationllc.com or on my blog at automationprimer.com. So before we get into the topic for today, I do like to describe a little bit of what it takes to become an expert in automation. Some of the things that you need to know before you just start winging it and programming PLCs. Of course, when we start in school, we start with reading and arithmetic, reading, writing, and arithmetic, as they say. If we're lucky, maybe we get a little bit of physics in high school, learn something about electricity, maybe on our own. Of course, there's not much of an excuse not to do this. Nowadays, you have the internet. You can get all kinds of information on your own. You do not need to go to school to get a lot of this information, but it's kind of important to know in what order to study things. Where school is going to encourage you to learn all those basic things, but then as you start to specialize, when you're younger or as you attend a tech school, something like that, you may need to learn a little bit of physics, electricity, chemistry. Logic can help. A lot of logic is in terms of classical logic, kind of philosophy sort of things, but there is also just if A and B, then B and A, that sort of thing. There are a lot of technical subjects involving physics, such as fluid power, magnetism, how do motors work. The concepts of digital and analog signals are important to know. How communications work, especially some of the older types of communications like RS-232, serial communications, what are baud rates, things like that. How do sensors work? What different types of sensing methods are there? As we advance a little bit farther, we can take our motors into motion control, which involves servos and encoders, which are a type of sensor. Learning numbering systems are very, very important. That goes along with digital and analog. Basically, a lot of this together involves controls of some kind. And there are different facets of controls, such as process control versus machine control. Of course, nowadays you learn a lot about computers anyway in school, but how do computers work? What are their different parts? How do you code on a computer? And then as you get into machine control, learning things about machine safety, possibly machine vision. Again, you notice how the different levels of this pyramid get smaller and smaller as you specialize more and more. So you need to know reading, writing, and arithmetic on the bottom level, but as you get a little bit higher up, if you're in process control, it's less likely that you're going to need to know machine vision and that sort of thing. PLCs, Programmable Logic Controllers. This is our topic for today, but something similar to that is a distributed control system, or DCS system, which usually is used more in process control. It handles lots of analog signals. That's an important topic to know. Robotics, again, apply more to machine control than they do to process control. Very important topic. HMIs used just about everywhere in machine control and in process control. Something that's kind of newer is the industrial Internet of Things, edge computing, low-level computers, edge devices, sensors with a little bit extra smarts in them. You definitely need to know something about IT today, IT and networking, because almost all of the communications between platforms, and especially large quantities of data, involve networking and usually some form of Ethernet. SCADA, very important, system control and data acquisition. That is a topic entirely on its own. As you get into the enterprise level of plants and things like that, you do need to know ERP, Enterprise Resource Planning, and Manufacturing Execution Systems, known by their acronyms ERP and MES. You need to know something about some of the high-level languages such as C and Python. Java might be important to you depending on which platforms you're using. Learning about databases can be very important. Another new topic would be AI, very important. Artificial intelligence. You can use this to help yourself, and then of course they are going to start building this into a lot of platforms where you will need to learn how to use it and how it works. And then ML is an abbreviation for machine learning, and a lot of devices do have ways of improving their own program. Machine learning, it can actually learn, such as machine vision. Some of the platforms will learn the different objects and become better as they modify their own program. And the reason that I put the little question marks up at the very top is because what you study next is kind of up to you. You will possibly specialize in something. You do need to know all these general topics if you want to be a good, well-rounded engineer. But as you move on, you will possibly specialize in some specific thing and become an expert in that. So all of these topics are, of course, available at the Automation Academy in some form or another, and I hope to keep adding to these topics. They are very important, and hopefully this little pyramid will be useful to you. So today's topic, I'm going to stay on this screen pretty much throughout this entire topic. We're going to be talking about the history of PLCs. And before there were PLCs, in the 50s and 60s, most control was handled by using relays. You would wire relays together to do certain automated tasks. If you push a button, for instance, maybe a certain relay would pull in and hold in and maybe run a timer. Timers were at that point not solid state. They were usually motor driven, or they could even be pneumatic in nature. You could have a diaphragm, and as the air passed through it, eventually the diaphragm would collapse and trigger a switch, and the switch would close, and again, hold in some kind of a relay and do some kind of control that way. So you could do much of what's done with PLCs nowadays, except that you had to use mechanical devices, such as relays and timers. Counters were also mechanical in nature. They did have electrical components within them. Some counters are, of course, entirely mechanical, and they simply count up and count down. But usually there's some kind of a contact closure in concert with the count being achieved. So you could count up to a certain point, and then a contact would close. Same thing with the timers. When the time would expire, with a motor or something like that, a contact would close, activating another relay, and you could creatively wire these relays together. And usually you did that design on paper. You would draft it, and you would connect these relays together in such a way that one relay would activate another relay under a certain set of conditions. You would use sensors like, at the time, limit switches, much more common than photo eyes. So you really had to contact the product in a lot of cases because we didn't have all the solid state electronics that we have now. In 1968, a bunch of engineers at General Motors in the United States presented a paper at the Westinghouse conference, and they detailed some of the problems they were having with reliability and documentation of the machines. As you can imagine, a lot of these relays all connected together were difficult to document, and then when people made changes, they might connect wires to different points. They had to document those, and just like today, they would sometimes leave out some of the documentation, and the technicians or maintenance people had to figure things out themselves and hopefully redline their drawings. But before we had CAD, the only way to really do this was to write it down on paper. So they had a lot of different problems with maintaining their control systems, and they kind of proposed, wouldn't it be cool if we had some kind of a electronic machine controller? At that time, computers weren't totally new. They had had computers since the 1940s in some form or another, but they were really huge and they didn't have a lot of memory, and a lot of them were also relay based, and sometimes had some kind of tubes inside of them to do logic. Tubes were a little bit quicker than relays. You didn't have to close a contact so much. You could just pass electricity, much like our solid state devices work nowadays. But relays were slow. You would have problems with the time that it took the contacts to physically close. And so they concepted the idea and proposed a design criteria for something called a standard machine controller. And the person who did this was an engineer named Bill Stone, and he worked for GM. And he listed a bunch of different criteria that the design would need to include to eliminate the scrapping of the assembly line every time you would do a model changeover, and you could replace some of the unreliable electromechanical relays with a little bit more reliable magnetic core memory, that sort of thing. So these weren't unknown components at the time, but nobody had combined them together into a formal machine controller. They wanted to extend the advantages of static circuits to 90% of the machines in their plant. So they wanted to get rid of the giant relay panels and create some kind of machine controller and put them in most of their machinery. They wanted to reduce machine downtime related to the control problems, make it easier to maintain, and most importantly, easy to program, change the program. And they would use the already accepted relay ladder logic that they had used for years to design the circuits. So you were going to use the same idea as you used for combining relays together in your logic. They definitely wanted to provide for future expansion, make things easy to change, be able to add I/O, and it had to be modular so that you could exchange components and expand it. It had to work in an industrial environment. At that time, of course, you didn't have air conditioning in most of the plants. You had dirt and moisture, electromagnetism, you had vibration on the machinery, so that was a problem. And you needed all full logic capabilities, including things like timers and counters. And they wanted to somehow be able to make it efficient. And they didn't, at that time, code in data reduction functions, which were making things simpler automatically. You had to do that by hand. You had to design it in. And they sent this specification and a proposal request to build a prototype for this. And they gave them to 4 different controls builders. And one of them is very well known today, a company called Allen Bradley. And at that time, they were through a Michigan-based company called Information Instruments Incorporated. Another company you may have heard of that they passed the spec to was the Digital Equipment Corporation, or DEC. And DEC became later important in designing of larger computers, mainframe computers, that sort of thing. Century Detroit was mostly a automotive-based company, so they were already doing relay panels and things like that, and they really didn't have the capability of inventing a machine like this, so they were out of the running pretty quickly. And then there was a fourth company called Bedford Associates. And Bedford Associates was a fairly new company. They had done some projects in Massachusetts, but they were familiar with some of this control technique that was used in the automotive industry. The DEC team, of course, with their background, brought a mini computer to GM, which was rejected. And a big reason for this was that there wasn't any static memory in the controller. So they needed some kind of method of storing static information that wouldn't change. If you powered everything down, you would lose all of that information. Allen Bradley was already a manufacturer of relays and rheostats and motor controls, that sort of thing, mostly motor starters, very classic contact closure type equipment. And this new idea was going to compete with their basic core businesses, which was electromechanical relays, but they went from a prototype into a production unit in only 5 months, which was pretty quick. The first attempt that they made for this program was the Program Data Quantizer, or PDQ. And the first one wasn't quite what they wanted, so they actually created a PDQ-2. And this was too complex and difficult to program, and was very big. And then they came out with something a little bit later after they'd already sort of lost the shot at the first contract, and they came out with the PMC, which was the Programmable Matrix Controller. It was smaller and it was easier to program, but it was still not sufficient for GM. At the time of this design criteria, Bedford Associates was already working on a design. Their system was going to be modular and rugged. It had no interrupts for processing mapped directly into memory. And this was their 84th project. They had already started before they received this specification. And so they decided to name this processor the 084. And you may recognize that because later came the 184 and the 284, and they just kind of kept that numbering system. There were several people on the design team, and you may have seen that at the beginning of this, and that will be in the show notes for the podcast version of this. The people that were in the picture were Richard Morley. He's known as the father of the PLC. Mike Greenberg, Jonas Landau, George Schwenk, and Tom Boisevane. I hope I pronounced his name correctly. And they got some funding and formed a new company based on this platform called Modular Digital Controllers. And you may recognize that acronym also, which is where the first name MODICON came from, Modular Digital Controllers, MODICON. The MODICON 084 was built ruggedly, had no on-off switch, which is interesting, no fans. It was totally enclosed, and outside air was not allowed to enter the system for fear of contamination, because this was a well-known problem where things would get stuck in the contacts of the relays and corrosion could be a problem. So they enclosed everything, and they kind of, Dick Morley had an interview and described some of his thinking behind this. He said that the programmable controller could be something like, imagine to be beneath a truck in the open and being driven around in Texas and Alaska, that sort of thing. So it had to be able to withstand dust and dirt and high temperatures and low temperatures. They really wanted it to survive. That was the most important thing. The other requirement was that it stood on a pole, helping run a utility or microwave station, which was not climate control and not serviced at all. Of course, this was before the GM specification. So they had different plans for this, possibly for controlling utilities in remote locations. But in 1969, Bedford and Associates and MODICON demonstrated the 084 programmable controller to GM, and they won the contract. And the controller consisted of three components. It had a processor board, it had memory, and then it had the logic solver board, which used a form of ladder logic to solve the algorithms. Of course, at that time, you didn't have graphical operator interfaces, anything like that, so you still had to enter it as mnemonic code. You had to put letters in and type things in. You didn't even use a typewriter necessarily for that. I'm not really sure what they used for the first programming technique, but it was obviously easier than the Allen Bradley version of it. So at that time, there was probably some kind of a handheld controller that you would enter your instructions in. And their original machine only had 125 words of memory, and it didn't need to run particularly fast. And in Dick Morley's interview with Howard Hendricks, he said, "You can imagine what happened. First, we immediately ran out of memory. And second, the machine was much too slow to perform any function anywhere near the relay response time." Relay response times, I mentioned this before, is the amount of time that it takes for the coil to be energized and then the contact to close. And that's somewhere around a 60th of a second. And the reason for this is, of course, 60 hertz. And everything at that time was pretty much AC. And many of these cabinets full of relays, you would transform the code into a lot more than 125 words. So they did expand the memory to 1K when they proposed it, and then they went to 4K. And at 4K, that was the initial Modicon controller, the 084. It lasted for quite a while. It had 16 and then 32 inputs and 16 outputs. And of course, they made it expandable where you could put more I/O, and you had to have memory associated with the I/O also. This was used by GM for several years. And of course, Allen Bradley kept coming out with new versions. They had the PDQ2 and they had the PMC. And then finally came out with something called the Programmable Logic Controller. And they immediately said, well, that's our new name. They did at that time also create a programming computer. So they were the first to do that. But the PLC itself, Programmable Logic Controller, came out in 1974. At the same time, GE was already working on a programmable controller. In 1971, they came out with something called the PC-45. It was not super widely adopted yet, but then their next platform, the Logitrol, was beginning to be used, of course, mostly by GE themselves in manufacturing. Meanwhile, the Japanese came out with their own controller. The first Japanese company to do this was Omron, which is still in existence today. They had something called the Sysmac M1R, and they still use that Sysmac name today. So this is a platform that has stood the test of time also, and several other Japanese companies came out with PLCs at nearly the same time. Japanese companies combine together in a lot of cases in zaibatsus, which are combinations of companies that can work on things together. And Omron is one of these, a zaibatsu that already made things like relays and timers and that sort of thing. So it was very easy for them to get into this. Modicon came out with both the 284 and the 384 in 1975. The 184 had come out in 1972. Meanwhile, Gould, which Gould was well known for control components at the time, purchased Modicon in 1977. And then in 1979, Modicon came out with a communication protocol called Modbus, and you may have heard that before. That is very popular still today across various different platforms. AB came out with a competing product also in 1979 called Data Highway. And Data Highway also stood the test of time and was used well into the 1990s and has pretty much disappeared. They did come out with something called DH Plus a little bit later that was simply faster And then Allen Bradley also came out with the PLC-3 in 1980. But the PLC-2 and PLC-3s were already in a lot of automotive plants in Michigan at that time. The standard Sysmac Omron came out with in 1977, improving on their platforms. They did come out with another communication protocol called HostLink later, and this allowed to do remote I/O, that sort of thing. Siemens entered the fray in 1976, and they came out with something called the S3, and there was an S series controller before that used in Germany, but the first commercially available SIMATIC that was out there was in 1976. And then the S5, which was a long-time platform for Siemens, very powerful, came out in 1979. And it kind of made a big impact in Europe. It became very popular there and became the base of a lot of European other controllers. And you'll see that if you start looking at things like Bosch and B&R and some of the different platforms. They had used much of the same techniques that the SIMATIC S5, and indeed the S7, which came out all the way in 1994, used a lot of the same timer techniques and things like that as the S5. S5 came out with a version of it called the 135U in 1984. Meanwhile, another one of those Japanese Zaibatsus, Koyo, started manufacturing PLCs both for themselves, for the Japanese market, and also for other people. And so GE came out with a model, the 300 series, in about 1985, and they had Koyo manufacture that. And meanwhile, Siemens also did the same thing. The SIMATIC TI 305 was about the same thing as the Koyo 300 series. So GE, Siemens, Koyo, Texas Instruments, which was not one of the major players, certainly isn't today in PLCs, but they also had a TI 305. And that was also manufactured by Koyo. And these all use the same programming techniques, same instruction sets, that sort of thing. Meanwhile, Modicon was still chugging along. They came out with a very powerful controller in 1986 called the 984. And the 984 kind of stood the test of time well into the 90s. The GE 9030, which was a pretty powerful platform for them, came out in 1990 also. And at the same time, computers, PCs were starting to become pretty standard and lowering in cost. So there was DOS software that could program most of these controllers. Now, DOS was still not a graphic programming language. You still had to type things in, but people could have their own laptops and a small screen, that sort of thing, and you could have a keyboard and type in the mnemonic instructions. You didn't have to buy a handheld controller, or Allen Bradley had a giant controller programmer that had run around on you would put it on a cart because it had a big cathode ray tube on it, big TV set, and you would have to wheel it around the plants. And when I got started in industrial automation, that was pretty much where PLCs were. I started in the late 80s, early 90s, and I would see these carts being wheeled around the plants, a lot of the manufacturing facilities. So what was interesting about that time was everything was pretty much still low memory, pretty hard to program. You did things with mnemonics. You would design things on paper. You would write your circuit down, and then you would code it into the controller by changing the pictorial representation of ladder logic, which again is relays and timers and counters, that sort of thing, in sequential operation, and you would turn it into a mnemonic set. And when I learned my first PLC platform, I learned Eagle Signal and Omron first, And I went to the Omron classes, and they had a handheld controller. You would draw your circuit, and then you would type things like load, and you would put an address in it. And if you wanted to fire an output, then you would say out, and you would put your output address. And you had internal memory also, of course, internal relays, which the original Modicon went all the way back to that. It had internal memory. But the original Modicon had 4K for everything. It had the program memory, the I/O memory, the internal relays, the logic, everything had to be contained in 4K. As things improved, it got up to, say, around 16K. And when I say K, I'm talking about kilobytes, which are thousands of bytes. Actually, a kilobyte is often kind of rounded up. It's 1024 because of binary, right? 1 plus 2 plus 4 plus 8. And one of those multiplication values is 1024. So 1K of memory was actually 1024 bytes of memory. Now, a lot of these different platforms, what was interesting is some of them, like Modicon, stayed with the 8-bit or 1 byte memory platform basis, and then Allen Bradley early on migrated to a 16-bit because they recognized that 16-bit words would allow you to put up to 65,000 values, especially when it came to negative numbers. That became a very important thing. So timers back in the 1990s were generally 0 to 32,767, which is basically your binary 2 to the 15th power. And the reason it didn't go up to 65,000 some odd 384 is because you had to be able to represent negative numbers, so they used signed decimal notation. And this allowed you to go from negative 32,768 up to positive 32,767. So you had a wide range of negative and positive numbers to deal with. You could run your timers up to 32,000. Of course, this became a problem because if you were timing in milliseconds, you could only go up to about 30 seconds. So they used a time base. You could have everything from a 0.01 second timer all the way up to a 10-second timer, where one tick of the clock would be 10 seconds. And this allowed you to go to several hours or even days of timing. If every 10 seconds the clock is ticking off, that would be 10 seconds times 32,767. So as time went on in the 1990s, of course, PLCs had taken over most manufacturing applications unless it was something very simple, because PLCs were less expensive than wiring together all the relays. The cost of solid-state components had come down. PLCs at this point were pretty much all solid-state transistor-based since the late 1970s, early 1980s. So at this point, your PLCs were much smaller than the original Modicons and the Allen Bradley PLC2s. The PLC5 for Allen Bradley came out in 1985, and that was their big PLC that they would use for the larger factories. It had a lot more memory, but then in 1991, they came out with the platform that I really first used in Allen Bradley called the SLC 500. The PLC stood for Programmable Logic Controller, and the SLC represented Small Logic Controller. So at that time, this was the smaller version of the PLC-5. It had a slightly abbreviated instruction set, pretty much the same as the PLC-5, but they dropped some of the more complex instructions. You didn't have as much PID, things like that. You had regular PID, and the PLC-5 had an enhanced PLC PID instruction. The SLC 500 eventually adopted the PIDE also. The SLC 500, interestingly, came out the same year as the GE 9070. And Omron, meanwhile, came out with the CV series, which was, again, something I went to school on in the early 90s learned the C200H platform, which came out in about 1986, and the CV series. The CQM1 had come out in 1993, and I think that's when I took my first Omron class. So a lot of platforms kind of proliferated there in the 1990s. The PC S7 came out from Siemens. They had a computer-based platform. That was in about 1997. So at the turn of the century, the main platforms were probably Allen Bradley, I would say, Siemens. Schneider bought Modicon in 1997. They became pretty popular in Europe also. Schneider also had several other PLC platforms. Schneider actually bought Square D, which at that time owned Modicon. They had bought it from Gould. So all these companies started acquiring each other, kind of became interesting. And then the big boys remained. Siemens, Allen Bradley was bought by Rockwell in the 1980s. So Siemens, Rockwell, GE combined with Fanuc for their control components in 1986. So Rockwell, GE, Fanuc, Schneider, Siemens remained just Siemens. Mitsubishi became very popular also in the 1980s and 1990s, especially in Japan. I would say they were the widest spread platform used in Japan by Japanese engineers. And to this day, they seem to prefer Mitsubishi controllers. The Q series for Mitsubishi came out in 2001. And another very interesting thing, let's talk about two things that are interesting and of note here. In 1994, the International Electrotechnical Commission came out with a definition of what a PLC should be, and that was IEC 61131-3, which defined the instruction set, what timers should be, what counters should be, what are the different data types used in PLC programming. And immediately, a lot of the existing PLCs did not match that specification. So for instance, they said all timers will time in milliseconds. And of course, I mentioned before that at that time, timers were 16-bit and could only count up to 32,767. So they could not count in milliseconds without becoming a 32-bit timer. And you didn't even have the computers in a lot of cases to run the software that would dictate 32-bit operating systems. That came a little bit later. So around the turn of the century, 2000, most companies started coming out with totally IEC 61131 compliant PLCs. For Allen Bradley, this was the Control Logics series. They still kept the SLC and the PLC5. They did have the Micrologics, but the Control Logics L1 came out in 1997. And of course, in the United States, because Allen Bradley was such a big player, a lot of the automotive companies and major manufacturers started migrating into the Control Logics platform. Control Logics platform was a 32-bit system. Instead of using integer-based math, they would use 32-bit math, which was useful for things like real numbers. If you wanted to express a real number, you needed 32 bits, whereas before you would have to combine two 16-bit registers or 4 bytes. You could combine those 4 bytes together. And that's part of what made Siemens a little bit harder to program, because they would have to set aside your memory areas and define that these 4 bytes would be used to hold a real number, for instance. So memory was somewhat fluid in that way. You could assign your different data types into your byte memory, or M memory, as it was called. Meanwhile, communications was also getting more powerful. Most things were going to Ethernet at the turn of the century. The IEC 61131 really was probably the big thing that changed the direction of a lot of these controllers. Another thing that happened in 94 was Koyo came to the United States. There was a guy named Tim Homan. I was fortunate enough to meet him in the 1990s, and he started a company called PLC Direct and started mail ordering PLCs, fairly low-cost PLCs at the time, that were really just Koyo branded PLCs. Of course, I mentioned before that Koyo manufactured for Siemens and GE and TI. TI was really no longer a player by the late 90s. They got out of that business. But PLC Direct kept coming out with these 300 based controllers. And a lot of the other companies had left those behind. The TI 305 and the GE 305 were mostly gone. GE had moved to their 9030s and things like that. TI had mostly disappeared. Siemens was on their S5 controllers, so they really didn't use the TI 305 type controllers anymore, the Somatic TI 305. So PLC Direct all of a sudden was the major player for the Koyo PLCs. And they came out with a 200 series, which is a very small, competing with the Micrologix size controllers for Allen Bradley, or the 200 series for Siemens. So they had their own little 200 series. And then their 300 series was really along the lines of the SLIC 500 in size, kind of a mid-range controller, or the S5 and S7 size. And then their large controllers were the 400 series, the 405. And I got to work with some of those in the late 90s. I was, again, fortunate enough to work for a Koyo plant that was in our area, and they used a lot of direct Koyo PLCs, brand labeled Koyo, rather than being brand labeled PLC Direct. So mail order at that time was kind of a new thing, but you could get your PLC, in a day or two from Atlanta. Everything shipped from Atlanta. They had a pretty good tech support at that time, but they would not come to your site and help you with your application. You had to call them up and use remote tech support. So that was one of the things that kept Allen Bradley kind of in the forefront in the United States. They had a very powerful distribution network, and their technicians or PLC specialists could come from the local distributor and come help you. And they had a tech support, GTS, Global Technical Services, that would also come to your plant and help you, of course, for a modest fee. But Allen Bradley became the major player by far in the United States. Siemens didn't really start making inroads until well into the 2000s. They did have, of course, European manufacturers in the United States that would use Siemens, but it was pretty rare that American companies would use Siemens equipment directly and specify those in their controllers. So Allen Bradley, big player in the U.S. GE was a big player in the U.S. Mitsubishi and Omron mostly overseas. Panasonic, of course, had PLCs. A lot of the big electronic manufacturers, Hitachi and Toshiba, the Japanese electronic manufacturers, had some sort of a PLC. I mentioned the TI, Texas Instruments. That was an American electronics company. But Allen Bradley really drove most of the other players out of the market in the United States. It's estimated now that Allen Bradley may be up to 60 or 70% of the U.S. installed base. And once you have an installed base, it's very difficult to change an entire plant over to a new platform. So 2000, all of these platforms began becoming 61131 compliant. Automation Direct rebranded, named PLC Direct by 1999, and came out with controllers that were IEC compliant. Now they have the productivity. They came out with a click somewhere in the early 2000s, I want to say. I was still using the Automation Direct, the Koyo 205 series for a lot of my applications at the end of the 90s for people that wanted a low-cost system and didn't want to pay for software. Software is pretty expensive for Allen Bradley and Siemens and even GE and even Modicon, Schneider. It was pretty expensive to get into the software. So for people that wanted lower cost PLC software, Automation Direct was a good platform. Omron software also not terribly expensive, and Omron became a major player kind of worldwide for OEMs. I've seen a lot of equipment come from Italy and Europe and even the United States manufactured with Omron PLCs, partially because the distribution network is really wide, and partially, of course, because of cost. It's a lot less expensive to get into the CS and CJ series than it is to get into especially the ControlLogix or TI Portal series. Mentioning the TI Portal, so Siemens was very powerful in their S7 series. It was still not completely IEC 61131 compliant, but then in 2008, 2009, they came out with an S7 1200, and mostly this was to replace the Siemens 200 series. So the S7 200 was replaced by the S7 1200. And along with this was a 32-bit, again, operating system, and you didn't have to worry so much about all the memory mapping. So TI Portal, totally integrated automation, is their newest platform. The 1200, again, was a smaller controller, but really did have a lot of networking capabilities. You could put a lot of remote I/O type devices on it that were Ethernet based. They had Profinet since about 2000, and so Profinet was a faster method of doing remote I/O control at that time. But TI Portal is today still their main platform for IEC 61131 compliant PLCs. Meanwhile, Allen Bradley had kept coming out with newer and newer versions of the ControlLogix. The L1 series was not terribly successful. The L55 series was more so. It did not have onboard memory. You had to apply memory to it. But the ControlLogix L60 was really probably the first widely used ControlLogix system. And they had the 61 through the 65, and really the only difference between those different numbers, 61, 62, 63, 64, 65, is the amount of memory that was available. They went all the way from down to 2 meg of memory all the way up to 32 meg of memory. And before that, before they got into the IEC compliant platforms, the most powerful SLIC controller, for instance, only had 64K kilobytes of memory. So memory was still very expensive through the 80s and 90s, but by 2000, things started getting much less expensive. One of the things that I've noticed that was a big change, the PLC 5 and the S3 and S5s were kind of big metal controllers, especially the 400 series for Siemens was a big, heavy, very tall system, as the PLC 5 was. Even the PLC 2s and 3s were large rack systems. You could put up to 19 cards in a base rack, and then you could extend the racks out with these big metal kind of constructs and chain them together. And as things evolved, they got smaller. You didn't need as much space for all your I/O connections and things like that. A lot of your I/O also became remote in nature. Profinet was out. Ethernet IP was used by Allen Bradley primarily. Before that, there were a lot of different serial protocols. Profibus, of course, was huge for Siemens, and a lot of other companies also adopted Profibus. And Allen Bradley was still kind of on their data highway, and then they came out with something called DeviceNet at the end of the 90s, and DeviceNet was used for a little bit smarter I/O. You could daisy chain devices, and it would be pretty fast. It was along the lines of the speed of Profibus. So that was Allen Bradley's answer into the Profibus platform. Of course, Modbus was still widely used by a lot of other platforms. Meanwhile, even Mitsubishi and Omron had their own bus-based systems. They came out with something called Sysmac Link. They like that Sysmac name, so a lot of Omron devices had SysMac designations for their communication protocols. Meanwhile, the Allen Bradley controllers started getting more and more powerful. The L70 series came out in about 2010. They were about the same as the L60 series. They still had a 1 through 5, so 71 through 75. And their memory was the same as the L60, so 2 meg through 32 meg. But they had an onboard USB port, so that was pretty powerful. And then the L80 series came out in about 2016. And that's pretty much where we are today. The TI portal is the main platform for Siemens. They're encouraging everyone to migrate from the S7s, even though they are in a lot of plants, S7 300s and 400s. They're encouraging people to migrate, plants to migrate into the TI portal platforms, the 1200 and the 1500s. Controllers are getting much smaller nowadays. Meanwhile, Mitsubishi has come out with something called the IQ series, very powerful, about 2014. Their software's gotten better also. That's one of the things that I've noticed. The Automation Direct has some pretty good platforms. The Productivity series, Productivity 1000, 2000, and 3000 series are again a kind of a mid-range PLC platform. Another thing that was very important came out in 1994 was a system called the Control Design System, CODESYS. So CODESYS, 1994, started becoming the base of various different manufacturers who didn't want to develop their own programming system. So they kind of came out with a standardized control design system. Some people call it CODESYS, some people call it CODESYS. It was originally control design system. Now it's just CODESYS. A lot of people pronounce it that way. And a lot of manufacturers, I think there's somewhere around 500 different manufacturers that are using CODESYS as the basis for their PLC control. Now, they will come out with different programming platforms for CODESYS and label it something else. For instance, PLC Engineer is something that is used by Phoenix. Wago has their own platform for CODESYS, and they name it something else. Another company that I didn't mention but was very important came out, I believe it was founded in the 80s, but became a little more important in the 90s, was Beckhoff. Beckhoff was probably the first. I imagine, of course, the PCS7 was computer-based, but Beckhoff may have been the first more widely adopted actual computer that ran software, a soft PLC. So their basis was using something like Windows, right? Windows CE or Windows 10, and putting the control engine on an actual PC. And this allowed for other applications to run at the same time as the PLC program. They were very specific about what type of controls you could have on your operating system. It's Windows, but it's a severely modified version of Windows, and of course it matches their hardware. But Beckhoff now has become pretty common in PC controlled systems. It really is a computer, and you can do things like put a database on your Beckhoff controller. So it also evolved from using a CODESYS system. So in the 90s, they had combined with the same system that Wago was using, a CODESYS, and that was TwinCat 2. TwinCat 2 kind of evolved into TwinCat 3, and they started running it on, again, a Microsoft Visual Studio platform rather than running it just on basic CODESYS. It looks very much the same, though. So a lot of these CODESYS-based systems, if you learn Beckhoff TwinCat 3, you will also understand how CODESYS works. It looks very much the same, since that's what it evolved from. And that's kind of where we are today. I'd say the biggest change over from 1968, 1969 was that there were only, 4 players in the very beginning, and some of them didn't even continue with their offerings. I'd say by the 1980s, maybe there were 15 players in the market. Different electronics companies had come out with their own versions of programmable logic controllers, but now could be up to 1,000 or more manufacturers that have some kind of a PLC. As a matter of fact, you can get a Raspberry Pi controller or an Arduino controller, which are little computers that run on things like Linux or different operating systems, and you can put a PLC engine on all kinds of little controllers and program it in something like ladder logic or any of the other 4 or 5 other languages that are defined by the IEC 61131. That was another thing that in 1994 they defined is what are going to be the final languages that we're going to use for PLCs. Everybody needs to start migrating to this. Of course, ladder logic was there. Something that ladder logic directly converts into is something called instruction list. And instruction list is a little bit different depending on which platform you have. I mentioned before that you would have to type things in like load A and B, right? If you wanted to do an and statement, and then out C, some kind of an address, maybe a physical address or an internal memory address, you had to code it into your ladder logic into some kind of mnemonic text. And Siemens took this to a much higher level. They came out with something called statement list. Statement list was like instruction list on steroids. It was more than just a intermediate language to convert to get it into the controller. It was actually a programming language on its own in the 1980s and 1990s. It became very powerful. But the IEC has deprecated instruction list anymore. One reason is that it's a lot harder to put all your code in there at such a low level language. Instruction list looks something like assembly. It has a lot of 3-letter and 4-letter acronyms that stand for different things, and or out, that sort of thing. And it differed from platform to platform. So that's mostly gone, but there are 4 or 5 other languages depending on how you define them nowadays. Function block diagram was something that was a graphical language that companies like LabVIEW, which was another computer-based platform, used pretty widely. So people kind of understood what function block was, and that has propagated into becoming an IEC language, very powerful language. A lot of people like using that for things like safety systems. It's graphical like ladder logic is. Of course, ladder's still in existence. And then there are a couple of text-based languages, one of which is structured text. And still different companies call structured text by different names. So if you're in Siemens, they would call it, let's see, it's not SFC, it's not STL, what is it? SCL, Structured Control Language, right? SCL is what Siemens calls their version of structured text. So even when you get into these standardized languages by the IEC, they do differ from platform to platform. Some structured text-based languages have different delimiters like a colon or a semicolon, different ways of expressing things. But most things are gravitating into something like what you see in Codesys. Their version of structured text is becoming pretty widely adopted. It's a little bit different than the Siemens and Allen Bradley versions of it. Most of the other platforms still out there, still have all the different languages in them, sequential function charts, that sort of thing. But I would say the major players are the ones that I've still listed. Modicon's still out there. Schneider owns them. A lot of them just are called Schneider PLCs now. Omron, still a big player out there. Mitsubishi, still a big player. Siemens and Allen Bradley, maybe the 2 biggest in the world now. GE You know, they have controllers out there and they're still widely used, but they definitely are not inexpensive, and they really haven't kept up, I don't think, with the software end of things as much as some of the other platforms. Allen Bradley, because they had such an installed base in the United States, is really the major player still in the U.S. And they've made inroads overseas, but they're quite expensive. So some of these smaller manufacturers are getting to play in the current industry also. I don't know what the future holds for PLCs, programmable logic controllers. I would say controllers will become smaller and possibly more distributed because processors are becoming more and more powerful. We have something called Moore's Law that really for many years was pretty accurate, where every year technology would effectively double. And that's slowed down a little bit just due to size constraints. I don't know that memory, for instance, doubles every year, but it's certainly a lot less expensive than it used to be. But still, Allen Bradley and Siemens controllers are still quite expensive. And what I've found very interesting is, for instance, the L80 series for Allen Bradley, L81 through 85. I would say your L85 may be double the cost or more of your L81 series, and the only difference is the memory. So they've gone from three megabytes on the low end up to 40 megabytes on the high end. And there's really no justification for why you would double the cost of the controller when you have memory sticks that go up to a terabyte of memory, right? And really what they're talking about with solid state memory is not terribly expensive. But again, they have, Allen Bradley has a monopoly on Allen Bradley. That's the way I always put it. So that's kind of my history up to this point. The little chart that you may see in the show notes or here on the screen for this webinar is available in my original book, the Advanced PLC Hardware and Programming book, which I put out in 2019. It has this timeline on it, and I may update this at some point. Beckhoff is not mentioned, for instance, on here, and I really should have put it on here. But in 2016, I wasn't doing a lot with Beckhoff, didn't know a lot about it. These are some of the different platforms that are out there, some of the pictures that you see on this screen. And I will again put this in the show notes for the podcast. You can see Allen Bradley. This is a ControlLogix controller. Siemens, Schneider, Modicon. These are fairly modern versions of everything. This is the Productivity series for Automation Direct or Koyo. I put some of the smaller manufacturers here like IDEC or Bosch. They are not as big of companies as Allen Bradley and Siemens, but they are still major players in the U.S., and they do have fairly similar looking PLCs, as you can see here. Mitsubishi still coming out with controllers. This is a fairly modern GE controller. And then on the left here, I put this is one that's actually in my shop. This is a Raspberry Pi that runs a PLC program on it and has devices from Pi plates that allow you to do I/O. So this is really meant to be an illustration that you can have a PLC that costs, say, a couple $100 and has a bunch of I/O associated with it. There are a lot of micro PLCs out there in the, say, $200, maybe $100 and some dollar to $300 range. Some of the other players that I listed are Phoenix Contact. They have the PLC Next, PLC Engineer software platform. Opto22 has the Groove system, and these are both Codesys-based platforms. And I kind of left the statement up here, the following are the opinions of Frank. Well, everything that I say here is just the opinion of Frank. You don't have to take it that seriously. So there's some of the different controllers that are out there. A bit of an update on my used stuff. So you remember, if you follow my YouTube channel, I put a lot of this and how everything was being cluttering up my shop space. There's a PLC 5 there in the upper right. and an old panel view HMI with some buttons on it. I still have all this stuff. You can see all the carts and everything, but I have put it in a separate building. So I do have a little storage space outside of my shop now. I have all the carts in there. I have everything organized, still not very well inventoried, but I do plan on putting this up for sale. I may keep a little bit of it, but a lot of this will be on eBay. That's probably going to be my best method of selling some of this and making it available to people. I think ultimately the people that might want some of this older, PLC 5 and Slick 500 type equipment. This is all Allen Bradley, by the way. There is no Siemens or anything like that on here. This is all Allen Bradley equipment that was acquired by Automation Training from Automation Training. The Canadian company bought the American company, and it ended up at my place here, and I am going to be putting it up for sale for Automation Training in Canada. And this is kind of what it all looks like. So still organizing things, putting it on shelves, that kind of thing, and cleaning it up as needed, testing it as needed. So that's kind of where I'm at with all my used stuff. Something that is going to change, I kind of mentioned that at the beginning of this webinar. There is a new podcast that I am putting out called Mastering the Machine, same name. It is going to be really audio based, as most podcasts are, but it will have a video component. I will certainly have to speak live in a lot of cases. I have some kind of a camera on me or something to do the podcast. But this podcast, this webinar, will actually make its way in pieces into that podcast. I plan on doing a general history podcast and probably taking pieces of this, depending on how this works out, and putting it on that podcast. But I'm doing 5 episodes, the first of which will be released on, I believe it's July 28th, which is a Tuesday. And there will be one episode come out every Tuesday, and it will be pretty much a standard podcast talking about different topics related to industrial automation. But I plan to make this webinar, this live webinar that we do here, a once a month open discussion forum for anybody who wants to kind of appear on the podcast. So we'll be able to talk about whatever you want to talk about in addition to whatever I come up with as far as topics. So these are some of the cover arts that were created for this podcast. I'm still in the process of putting it together with some help, professionals, because I am not particularly professional at doing all of this. So these are some of the logos that came up. It will be 20 to 40 minutes long, and they'll be released weekly, but I will be able to kind of batch create them. The difference between a podcast and a webinar, a podcast has an RSS feed, and what that means is that people can subscribe to it. It will automatically, the episodes will appear in their method of choice, right? So their phone or their computer or whatever. There will be a press release. I really need to complete some of these before the press release goes live. Again, I'm a little bit behind the curve. There will be some kind of a newsletter. I'm not exactly sure what form that will take. I really need help with this. I can't do this all by myself, and I can't really afford to just pay other people to do it all the time. It doesn't create any income for me, so I don't really have an easy way to fund it. But it will have its own webpage on the Automation LLC site, and then hosting, will somebody else be guest host? Don't know. Guests? Well, certainly. I will definitely have guests whenever possible. I want to try to make it automation focused, but I may do some things on entrepreneurship and like this, history, that type of thing, talk about different types of technology. But overall, I'm going to stick to the topic of industrial automation with a little bit on there about running businesses, since that's what I've done for the last however many years. So the next webinar, it will probably be an open podcast version of this webinar. So the topic unknown, it may just be a general discussion, but it will be, as far as I know, on August 9th, 2025, barring any unforeseen incidents. I will have a live webinar, and anybody can attend, and we can talk about various automation related subjects. You can ask questions, and these will still be monthly open, but they will combine with the podcast that's going to be coming up, the Mastering the Machine podcast. For all who are watching this live, thank you for attending. For all who see this on YouTube, I hope you got something out of this. I'm sorry for some of the little foibles and misstatements that I may have made during this. This was my attempt to try to create something that was not as video intensive as a webinar would be, so that I can use pieces of it in my upcoming podcast. I hope to kind of butcher this and take pieces of it as needed for the Mastering the Machine podcast. So thank you everybody who attended, and we'll see you next time.